The first part of today is going to be devoted to the model kinetics, and it's probably going to be the most lengthy lecture we're going to have. Just because, before I do that, does anybody have any remaining issues or questions from yesterday? Okay, enough said. You should have, I think you will have downloaded either a PDF or a Word file, which will simply be called chapter2.pdf or chapter_2.pdf. That is from the present in-press Chesapeake Bay report. So that's as up-to-date as it gets. Okay, so that reflects exactly the Chesapeake Bay model that's in use at this minute. This is the same conservation of mass equation that we looked at yesterday. I'm just going to mention that today we're really looking at the source and sink term. And when we look at equations for the kinetics, I'm going to drop all this other transport stuff and just really look at the rate of change in that source and sink term, just so I don't have to copy all of that repeatedly. We'll start here. The model is built on a number of cycles. A carbon cycle, a nitrogen cycle, a phosphorus cycle. We used to have a silica cycle. You might talk about a dissolved oxygen cycle. So these are the things that make the model, these are the things on which the model is based. And probably the most important is the carbon cycle. And if you even want to rank things again, the most important thing in the carbon cycle are the phytoplankton right here. Let's look at the carbon cycle for a few minutes. This, the way this box is organized, if it's in a square, those are model state variables. So, for example, the model state variables include 3 alkyl groups. Model state variables include dissolved organic carbon. Model state variables include particulate organic carbon. If there's no box around it, it's not really a model state variable. And then these arrows include various sources and sinks or various transfers between state variables. So, for example, algae, when algae die, they don't go to heaven, right? They go to dissolved organic carbon or particulate organic carbon. So mortality creates dissolved or particulate organic carbon. Particulate organic carbon undergoes a process called hydrolysis, or we name it hydrolysis. It dissolves effectively. Respiration takes dissolved organic carbon and converts it to inorganic carbon. We represent respiration, okay? That's oxygen consumption. It's very important. We do not, in this particular model, worry about dissolved inorganic carbon. So effectively, the dissolved organic carbon, when it decays, just disappears from our system. We have settling of particulate organic carbon. It settles into the benthic sediments, and we heard yesterday a lecture about the sediment diagenesis model. Algae, through photosynthesis, they create carbon. And again, we don't worry about, in this particular model, we assume that the supply of inorganic carbon is infinite. We don't worry about it. And through respiration, they produce inorganic carbon. When we designed this model, and even now it's somewhat different in that algae are quantified as carbon, okay, in the model. Now, it's interesting because when you take out phytoplankton observations, you measure chlorophyll. But in the model, algae are quantified as carbonaceous biomass, so that's something to keep in mind. There's a couple of reasons for doing that. One rationalization, or one really good reason, is because we have this sediment diagenesis model, which takes carbon and oxidizes it into, creates sediment oxygen demand. So if our model is based on chlorophyll, it gets kind of nasty. I think there's still a lot of models out there where the actual model state variable is chlorophyll, but that is not the case for this model, and as I said, I won't call it unique, but I'll say it's different from a lot of other models you're going to encounter. So let's go down a little bit here. I pretty much explained some of the state variables. Okay, so this is the algal, this is the equation that determines algal, the change, the source of sink, internal source of sink of phytoplankton. So the change, B is, you can think of as algal biomass, is growth minus respiration. In this case, BM stands for basal metabolism. Oh, great for office. We'll just hold on for 10 seconds here. Oh, okay, there we go. Settling. And out here is a predation term. So this is pretty standard stuff. It gets unstandard pretty, or non-standard pretty quickly, but particularly when we look at this, this growth term.
I'm sorry, Carl, just a quick question, and maybe a correction. The B is multiplying the settling rate as well, the way you're, right? Oh, sorry, B is the biomass. Never mind, sorry, I misread it. Sorry.
Okay, so two things determine algal production: the availability of light and the availability of nutrients. And if you want to subdivide, the nutrients that are required in this for these algae are nitrogen and phosphorus. So, okay. What we need to do is to okay, so we're going to look at this growth term first. What determines algal growth? To the best of my knowledge, the growth kinetics in this model are unique. And maybe other people now have replicated them, I don't know. But conventionally, most models, you give it the algal growth rate, and you might put a temperature modification in there or something like that. And traditionally, the growth rate's about 2 per day. We do not do that at all. So we have a very complex, hard to follow way of determining the growth rate. So we're going to look, this equation here is what we're going to look at. Why the heck, all right, before I go to all this trouble, why did we go to all this trouble? We were challenged or charged with modeling primary production in the bay to a high degree of accuracy. And what we did was we recruited some phytoplankton scientists. We did a lot of work in the literature. And what I'm going to show you are the parameters that phytoplankton scientists measure. Okay, so if you either go out and get somebody to measure these things for you, or if you, again, you know, pick up a book, of algal physiology book, you're not going to find the growth rates, okay? You're going to find things like, this is the maximum specific production rate. This is the grams of carbon per grams of chlorophyll per day, okay? You can create a growth rate from that, but that's what it is. So phytoplankton have a maximum photosynthesis rate. It's how many grams of carbon can be produced per gram of algal chlorophyll per day. And that is the model input value. And once again, if you can actually find this or derive this in algal physiology books. So, and then what this effectively does is this says, I'll show you a plot of that in a moment, but this little thing over here is the influence of light. Okay, so I think I have that down here. Next slide, there you go. This is a production versus irradiance curve. And once again, people who work in phytoplankton physiology, they create this production versus irradiance curve. So I is irradiance, light. And this again is our production, and what you see is it's sort of a rectangular hyperbola. When light is very low, The production rate is effectively a linear function of irradiance, and as the light increases, it more or less saturates until you get up to that maximum value. And this production versus irradiance curve is defined by two parameters. What we went over a few moments ago, this maximum specific production rate, and something IK. Actually, what defines it is the initial slope of the production versus irradiance curve. And this IK, when we saw this equation over here, IK, it is the intercept of the initial slope of the production versus irradiance curve and the saturated specific production. So go out to pick up that physiology textbook again. I'm trying to think of the one I used to use. I won't worry about it for the moment. And they will give you, for various species of algae or for various systems, IK and PB max. Okay? So again, we do this because this is what the things that algal physiologists measure, and these are things that you can report with confidence. Okay? You can employ them with confidence. So that's why we do this. I love it.
Quick question?
Yeah, go ahead, Jim.
No photo inhibition, though.
We don't measure it.
Right. I mean, seeing some production curves in Long Island Sound, there's a little bit of suggestion, maybe at very high radiance you may get a little photo inhibition, but this has worked out pretty well for the bay then. Okay.
Irradiance down here. So what are these units? E per meter squared per day, Einstein per meter squared per day. What's an Einstein? It's actually photons. It's how many photons are striking per meter squared per day. So it's not Langleys and it's not watts. It's photons. And the same people who measure Pmax and IK for us will measure irradiance in Einstein per meter squared per day. So on the other hand, well, we'll get into this a little later on, but I give you a preview. Go out and get your Met data and ask the Weather Service how many Einsteins per meter squared per day we had yesterday, and they're going to scratch their heads and say, good luck, you know. So we'll deal with that in a moment. Hey, we'll deal with it now. Photosynthetically active radiation, PAR, in Einstein per meter squared per day. And going across there is watts. That's solar radiation. That's energy. Okay, so that if you put out all right, that's something that's conventionally measured. Go to a physicist and he will tell you there is no relationship whatsoever between watts, which is thermal energy, and Einstein per meter squared per day. Okay, there's absolutely no relationship. That's the physicists talking. The empiricists, the engineers say, come on, there's got to be. I mean, you know, if we had a big sunny day yesterday and it was hot, we probably had a lot of Einsteins of that photosynthetically active radiation. And there's a relationship between measurements of thermal energy, watts that you can measure, and Einstein per meter squared per day, which can also be measured. So in fact, you know, what you see is there's a lot of scatter in that, but indeed they are empirically related, as they must be. So if you're looking for, you know, measurements of Einstein per meter squared per day, you might actually get lucky. You know, people at VIMS or at Horn Point have some records. On the other hand, if you don't get lucky, empirically you can convert it from things that are readily measured.
But I think we took a look at that, these micro-Einsteins, who were micro-Einsteins, Einsteins. We found enough stuff in the literature to be able to go through it, and I think, and I'll have to check somewhere on my computer, but I thought it was like 5.4 micro-Einsteins per Langley per day. So there was, you know, and that's another standard measurement. I think a lot of the radiation data is collected as Langleys per day. So there is, I'll check the number, but yeah, we came up with one, but certainly that seems like a pretty good relationship as well.
Yeah.
It'd be interesting that now I need to know what watts per Langleys are to make sure that my number checks with what you've got.
Oh, Lord. Well, anyway, empirically, you can get this stuff. What's the next slide here? Okay, so for a moment, okay, so let's go back to here. So we've dealt with light. And once you have, it's going too fast here. Okay, so what this says is that this PBM, that's the maximum specific production rate. That's when the algae are cranking, you know, that's the maximum. PB is the actual production rate given an irradiance I, okay? So
IK is a function of I.
IK is a function of the algal physiology. It's the intercept.
Oh, it's just the intercept.
Right.
Okay, it's not the value on that line you show.
Well, let's just go back for a moment. This is the production versus irradiance curve.
Right, so.
IK is where the initial slope intersects with the maximum.
Gotcha.
So
it would be 50, it's a constant.
it's a constant, yeah.
Gotcha. Okay, it's not represented by the line, it is a constant.
When you come to here, this is the actual irradiance
Yep.
on that day or whatever. And you can see if the actual irradiance is much, much greater than IK,
Sure.
this is a square root, this is effectively unity, and the production would be the maximum value. As if I is much, much less than IK, then the actual realized production is much, much less than the maximum.
So
Okay.
It's almost like a Michaelis.
Yeah, it is. It is. But for whatever reason, Jasby and Platt use a square root.
Yep.
It's just like a monad or whatever. So once you have the production rate, which is grams carbon per grams chlorophyll per day, you can convert that to a conventional growth rate if you know the algal carbon to chlorophyll ratio. Carbon to chlorophyll ratio is like 50 grams carbon per gram chlorophyll, something like that. Once again, it's a property of a specific species or something of algae. It varies. Lord, I don't even want to go into that, so I won't. But you can get, once you have this specific production rate, you can derive a growth rate for use in that conventional algal equation.